Waveguide Tees. A waveguide tee is a three-port device. They are used to connect a branch or section of the waveguide in series or parallel with the main waveguide. It is formed when three waveguides tube are connected in the form of the English alphabet T. Waveguide junctions are used in microwave technologies when power in a waveguide needs to be split or some extracted. Adjustable matching reactance can be introduced by means of a tuning screw at the center. There are a number of different types of waveguide junction that can be used. When selecting a waveguide junction, balances between performance and cost need to be made, and therefore an understanding of the different types of waveguide junction is useful. The major types are E-type T-junction, H-type T-junction, and magic T waveguide junction. E-plane T. An E-plane T is a waveguide T in which the axis of its side arm is parallel to the E field of the main guide. It is characterized by the fact that the output of this form of waveguide junction are 180-degree out of phase with each other. If two input waves are fed into ports 1 and 2 of the collinear arm, the output wave at port 3 will be opposite in phase and subtractive. From consideration of symmetry and the phase relationship of the waves in each of the arms, results are equal in magnitude but opposite in phase. That is, S31 is equal to S13, which is equal to minus S23, which is equal to minus S32, and S12 is equal to S21. The third port is called the difference arm. All diagonal elements of the S matrix of a E-plane T junction cannot be zeros simultaneously, since the T junction cannot be matched to all the three arms simultaneously. Considering matched port 3, the S matrix of E-plane T can be derived as follows, denoting the incident and outgoing signal variables at the ith port by AI and BI respectively. The net input power to port 3 is given by square of A3 minus square of B3, which is equal to square of A3 multiply by 1 minus square of S33. And the output power is B1 square plus B2 square is equal to 2 into A3 square into S13 square. Since the junction is assumed lossless, the input power must be equal to the output power, that is 1 minus square of S33 is equal to 2 into square of S13. By a suitable matching element, we can make S33 equal to 0, so that S13 is equal to 1 by root 2. From the symmetry characteristics as described in the previous slide, S13 is equal to S31 is equal to 1 by root 2 and S23 is equal to S32 is equal to minus 1 by root 2. Based on power consideration, S11 equal to S22 equal to 1 by 2 and S12 equal to S21 is equal to 1 by 2 for S33 equal to 0. Therefore, S matrix for E-plane T is given by S11 is equal to half, S12 is equal to half, S13 is equal to 1 by root 2, S21 is equal to half, S22 is equal to half, S23 is equal to minus 1 by root 2, S31 is equal to 1 by root 2, S32 is equal to minus 1 by root 2 and S33 is equal to 0. H-plane T. An H-plane T is a waveguide in which the axis of its side arm is perpendicular to the E field of the main guide. It is characterized by the fact that the two outputs from the top of the T section in the waveguide are in phase with each other. If two input waves are fed into ports 1 and 2 of the collinear arm, the output wave at port 3 will be in phase and additive. Because the magnetic field loops get divided into two arms 1 and 2 in a manner similar to currents between branches in parallel circuit, H-plane junction is called a shunt junction. For a symmetrical and lossless junction, in absence of nonlinear elements at the H-plane junction, the S parameters are as below. S11 is equal to half, S12 is equal to minus half, S13 equal to 1 by root 2, S21 is equal to minus half, S22 is equal to half, S23 is equal to 1 by root 2, S31 is equal to 1 by root 2, S32 is equal to 1 by root 2 and S33 is equal to 0. Because of mismatch at any two ports, the VSWR at the mismatch port of either E or H plane T junction is very high. Voltage standing wave ratio is equal to 1 plus reflection coefficient and 1 minus magnitude of the reflection coefficient is 3. Magic or hybrid T. A magic T is a 4-port waveguide T, that is a combination of E-plane and H-plane waveguide T. If two waves of equal magnitude and same phase are fed into port 1 and port 2, the output at port 3 is subtractive and output will appear additively at port 4. The magic T has the following characteristics. If wave is fed into port 3, it will produce an output of equal magnitude and opposite phase at port 1 and port 2. The output at port 4 is 0. Thus, S13 is equal to S31, which is equal to 1 by root 2, which is equal to S24, which is equal to S42, and S34 is equal to 0. If wave is fed into port 4, it will be divided equally between port 1 and port 2 in phase with no coupling to port 3. Thus, S14 equal to S41, which is equal to 1 by root 2, which is equal to S24, which is equal to S42, and S43 equal to 0. If wave is fed into one of the collinear arms at port 1 or port 2, it will not appear in the other collinear arm at port 2 or 1. Hence, two collinear ports 1 and 2 are isolated from each other. Therefore, S12 is equal to S21 is equal to 0. A magic T can be matched by putting tuning screws suitably in the E and H arms without destroying the symmetry of the junction. Therefore, for an ideal lossless magic T matched at ports 3 and 4, matched at ports 3 and 4, S33 is equal to S44 is equal to 0. Therefore, S matrix for a magic T matched at ports 3 and 4 is given by S11, S12, S13 and S14. S12, S21 is equal to S12 and S22, S23 is equal to minus S13, S24 equal to S14, S31 is equal to S13, S32 is equal to minus S13, S34 equal to 0, S33 equal to 0 and S34 equal to 0. S41 is equal to S14, S42 is equal to S14, S43 equal to 0 and S44 equal to 0. From the unitary property applied to rows 1 and 2 of the S matrix, we get S11 square plus S12 square plus S13 square plus S14 square is equal to 1. Equation 5. Similarly, S12 square plus S22 square plus S13 square plus S14 square is equal to 1. Equation number 6. Subtracting these two equations, we will get S11 square minus S22 square is equal to 0. Or S11 equal to S22. Equation 7. From the unitary property applied to rows 3 and 4 to S13 square is equal to 1, or S13 is equal to 1 by root 2. Equation 8, and 2 into S14 square is equal to 1, or S14 is equal to 1 by root 2. Equation 9. Substitute equations 8 and 9 in equation 5. S11 square plus S12 square plus S13 is equal to 1 by root 2, therefore and S14 is equal to 1 by root is equal to 1, or S11 square plus S12 square plus half plus half equal to 1. Therefore S11 square plus S12 square is equal to 0. Question number 10, which is valid if S11 equal to S12 is equal to 0. From equations 7 and 11, I can say that S22 is equal to 0. Therefore, S matrix for magic T is equal to 0, 0, S13, S14 equal to S13, S21 equal to 0, S22 is equal to 0, S23 equal to minus 13, S24 equal to S13, S31 equal to S13, S32 is equal to minus S13, S32 equal to minus S13, S33 equal to 0, S34 equal to 0, S41 equal to S13, S40 equal to S13, S43 equal to 0, S44 equal to 0. Where S13 equal to 1 by root 2 is equal to S14. Therefore, final S matrix for magic T is given by 1 by root 2 into 0, 0, 1, 1, 0, 0, minus 1, 1, 1, minus 1, 0, 0, 1, 1, 0, 0. Applications of magic T. The magic T has a number of applications in various microwave circuits, such as the EH tuner for impedance matching, balanced mixer in a microwave superheterodyne receiver, power combiner, and duplexer. In an EH tuner, both E and H arms are terminated by movable shorts which act as E-plane and H-plane stubs. The position of the shorts can be adjusted so that a wide range of load impedance may be matched to reduce the voltage standing wave ratio of waveguide system connected through the collinear arms. In balanced microwave mixer configuration, an incoming signal is fed to the E arm and a local oscillator signal is fed to the H arm. These two signals, when enter the collinear arms, the crystal diodes placed in these arms produce the IF signal or difference signal. The local oscillator signal from H arm will arrive at the diodes in phase, whereas the incoming signal from E arm will arrive at the diodes out of phase. These signals are mixed in the nonlinear diodes and produce IF signals in the collinear arms, which are out of phase by 180 degree. Since local oscillator noise will be in phase at the diodes, this gets cancelled at the balanced IF input, whereas the IF signals are added up in phase for amplification in IF amplifier. The duplexer is a circuit which works as both the transmitter and the receiver using a single antenna for both the purposes. Port 1 and 2 are used as receiver and transmitter where they are isolated and hence will not interfere. An antenna is connected to E arm port. A matched load is connected to H arm port, which provides no reflections. Now there exists transmission or reception without any problem.